Hey guys, welcome to Station 2 for this first day of talking about the atom. In this video, we're going to talk about the history of the atom, how our current model of the atom came to be, who helped develop it, and then we're going to talk about something called Coulomb's law, which is super important. Coulomb's law is one of those things that we're going to talk about all semester. Coulomb's law is your new best friend. So first, we're going to talk about the atom, and we are going to take it all the way back to super ancient Greece, to a man named Empedocles. So it was a pretty commonly held belief in all of ancient Greece that all matter is composed of 4 elements. If you thought for about 15 seconds about it, you might be able to come up with them, especially if you're, an Avatar fan. Are air and fire and earth and water. Depending on your choice in television viewing, these go really well together. Pretty much every ancient Greek believed this is what all matter was made of. We do specifically credit Empedocles with this. He was the first one to state it. And then you fast forward a couple of hundreds of years to just regular ancient Greece. We're going to talk about Democritus, and he is one of 5 scientists that you are going to be expected to know. So Democritus, he sort of threw out this whole earth, wind, fire situation, and he said that all matter is made up of extremely small, solid, indivisible, not invisible, but indivisible, meaning can't be divided, right? Just like the Pledge of Allegiance, one nation under God, indivisible, can't be divided. Particles that he called atoms. So that was Democritus. And this was in like 460 BC. So then thousands of years pass before anything changes at all. Enter John Dalton, early 1800s. He proposed an atomic theory. So that's a theory about the atom. He proposed an atomic theory with 4 postulates. A postulate is like a piece of a theory. It's like a baby theory. So there are 4 little pieces of his atomic theory, and the first one's going to sound pretty familiar. Postulate number 1 from John Dalton said all matter is made of tiny, indivisible particles called atoms, which cannot be broken down into smaller parts. And maybe you're looking at this and you're like, yeah, cool, makes sense. And maybe you're looking at it and thinking, that doesn't seem quite right. And if you are in that second group, you're right. This is not quite ideal. And we're going to talk about how Dalton's postulates changed over the course of history. But here's the deal. It's going to sound like we're picking on Dalton, and we're not, because what he did was amazing. In the 1800s, with very, very limited technology, he did incredible things in discovering the atoms. Basically, the stuff he missed were exceptions that he had no way of knowing about. So yes, we are going to talk about postulate number 1 again in a few minutes, and we're going to say, actually, he didn't quite nail it, but he still did an incredible job. Dalton, awesome dude. Postulate number 2, atoms of the same element are identical, meaning they have the same mass, they have the same properties, and different elements are different. Yeah, this is another one that's going to be a little problematic in a minute. Postulate number 3. Atoms of different elements can chemically combine together in whole number ratios to form compounds. And this is true. We spent a big portion of Unit 1 talking about compounds. Things like water combines in a whole number ratio of 2 hydrogens to 1 oxygen. Or glucose, another very important molecule, combines in a ratio of 6 carbons to 12 hydrogens to 6 oxygens, or 1 to 2 to 1. Different elements can come together to form compounds. This is definitely a thing. We spent a lot of time talking about it. And postulate number 4 says during chemical reactions, atoms are rearranged. All right, we talked about this in Unit 1 as well, right? Bonds are broken, atoms are rearranged, but atoms of one element cannot. be changed into atoms of a different element. We're going to see something in unit 13, our very last unit of the whole entire year, that sort of toes this line. It gets a little fuzzy, it gets a little gray. But this is pretty much true, and for the entire year, we are going to treat this one as true. So Dalton, he did a really good job, considering this was, I think, 1803 that he was doing this. So then, Dalton comes up with his 4 postulates, and about 100 years pass, maybe like 90 years pass. And we get Joseph John Thomson, J.J. Thomson, who was not the loveliest of people. And he performed the cathode ray tube experiment. The cathode ray tube experiment. Basically, he took a box. He took a box that was capable of producing a really high voltage. It was capable of producing electricity. And he passed it through this tube. And it started shooting across the tube what appeared to be a beam of light. But when he put magnets on either side of the tube, so like a positive magnet and a negative magnet, this beam of light started curving towards the positive magnet, which if you've ever, put a magnet out in sunlight, the sunlight does not care about your magnet. Light is energy. It does not care about magnets. So the fact that his quote-unquote light was bending in the presence of magnets meant it was not at all light. It was in fact matter. And it was matter with a negative charge because it was attracted to this positive plate. So with his cathode ray tube, J.J. Thomson discovered the electron. So he took this idea of the electron, this idea of this negative particle, and he created the plum pudding model. I'm not making this up. This is really what the model is called. Because in late 1800 England, they ate a dessert called plum pudding, which was kind of like bread pudding, which is milky, soggy, sweet bread. And they put raisins in it. They called them plums, but they were raisins. So we're going to see a picture of this in a minute, but just keep in mind, he named one of the biggest scientific breakthroughs over like a soggy bread dessert. It is what it is. So according to this model, you have your negative electrons embedded into a positively charged sphere of uniform density. All right, so his plum pudding model looked like this. You have your sphere that is just sort of a squishy mass with a positive charge. It's all one density all throughout. So that's the pudding. This is the bread pudding, this positive charge. This is your soggy bread. And then scattered throughout our soggy, squishy, positive sphere, we have our negative electrons. These are the plums. And again, a plum is like a raisin. He must have been real hungry when he did this. I don't know. So you have your negative electrons scattered all throughout this sphere of positive charge. You should have learned about atoms in middle school, and if you did, you know this is not what they look like. So again, Thomson did not nail it, but he made a really big breakthrough. So consider, how did Thomson's discovery contradict Dalton's postulates? And which aspects of Thomson's theory are still relevant today? You should be in groups with your other Station 2 people. Talk it over amongst yourselves. Think about Dalton, think about Thomson, compare the two, talk amongst yourselves, and then we'll go through it together in the video. All right, so the big thing that Thomson did, he proved that Dalton's postulate number 1 must be false. Not entirely false, but he disproved a big part of it because Dalton said atoms cannot be subdivided. Atoms are indivisible. But that can only be true if an atom is the smallest thing there is. Thomson said, actually, there's something smaller. It's called an electron. So atoms can be broken into smaller parts because there's something smaller than an atom. Atoms can be divided. They've got smaller pieces. They have electrons. So that was a big thing because Dalton's theory had stood for like 100 years. And even before then, we assumed atoms could not be divided. As far as aspects of his theory that are still relevant today, well, he said there are negative electrons. That's still a thing that you should have learned. Negative electrons are a thing. And while he was wrong about what the positive areas of an atom look like, he did say there has to be a positive charge. So there is a positively charged thing within an atom. He was just not quite right about what it looked like. So that was Thomson. And that stood for about, I think, 20 years. The plum pudding model was the working theory of what atoms looked like for about 20 years until Ernest Rutherford came along. And Ernest Rutherford did the gold foil experiment. Gold foil is like aluminum foil, but super expensive because it's made of gold. It's very, very thin. It's even thinner than aluminum foil. It's about 1 atom thick. So Rutherford took his sheet of gold atoms. They're all touching each other. I can draw. He took his sheet of gold atoms and he decided, I'm going to fire these things called alpha particles at my sheet of gold. Alpha particles, as far as, subatomic teeny tiny particles go, things the size of an atom, these are pretty large particles. So he's firing some large particles. They have a positive charge and he's shooting them at his gold foil. What he fully expected to happen, according to Thomson's model, each alpha particle should have passed straight through this mushy goop, dodged around the electrons, and just gone in a straight line, right? This is what he expected to happen. If you look back at our picture here, largely they did, right? Here's our beam of alpha particles coming through. Most pass completely in a straight line through your gold foil, but not all of them. Some of them are veering off in this direction, some are veering off in this direction, some are hitting the foil and bouncing backwards, which is not even a little bit what he thought was going to happen. So what must be the case is instead of just one mushy bread pudding goop of atom, there's got to be something very small and very dense and positively charged right in the center of the atom. So Rutherford and his gold foil discovered the nucleus. Some other important conclusions that he also came up with: the nucleus is real small and very dense. It's got to be teeny tiny because most of the alpha particles did pass through. Most things did not run into the nucleus. And it has to be very dense because it is heavy enough to bounce an alpha particle off of it. If it were like the atomic equivalent of wet toilet paper, the alpha particles will just go straight through, no problem. So it has to be very dense and it has to have a positive charge to deflect those positive alpha particles. And since most things pass straight through, atoms are mostly empty space. So Rutherford's model sort of took all of the positive from Thomson's model and squished it into the center. So now we've got this positive center surrounded by our negative electrons, which is getting closer to what we learned in middle school is what an atom looks like, but still not quite there. So once again, consider, how did Rutherford's discovery contradict Thomson and or Dalton? Compare Rutherford to both of the scientists we've talked about, and which aspects of his theory are still relevant today? Once again, talk it over. When you're ready to see the answer, unpause the video. All right, so as far as contradicting Dalton, once again, atoms are not indivisible. We already knew this because Thomson found electrons, but a nucleus is also a tiny piece of an atom. So atoms are super not indivisible. They've got all these pieces we didn't know about. And Thomson said that atoms were a uniform density and a positively charged sphere. That's not it. Atoms are not of uniform density. They're mostly empty with that tiny dense nucleus in the center. So atoms are not uniform in density. As far as aspects of Rutherford's theory that are still relevant, honestly, he did pretty good. Really, the only thing he messed up on were the electrons. So we've got that small, dense, positive nucleus. And the rest of the atom is mostly empty space. All right, then in the early 1900s, we had a couple of other scientists. Honestly, we don't talk about them too much. You don't need to know a whole lot about them. But after we came up with electrons in the nucleus, James Chadwick came along and he said, okay, well, the nucleus may be positive, but you've also got some neutrons in there with a zero charge, with a neutral charge. And then Frederick Soddy, right around the same time, he said, oh, by the way, there are these things called isotopes. And your group 1 people are going to explain to you what an isotope is, but basically an isotope are atoms of the same element which, as you may recall, had initially not been a thing. Atoms of the same element that look different, those are isotopes. So then consider, how did Chadwick's and Soddy's discoveries contradict some previous scientists? Everyone is contradicting Dalton. Dalton's just getting torn to pieces over here. For Dalton, atoms of the same element are not identical, or they don't have to be. Not every carbon atom is exactly the same. And then as far as the other scientists, no one had even considered the possibility that there was a neutral thing in an atom. So this neutral particle contradicted everybody leading up to it. But the big one is Dalton said that atoms of the same element look the same, and that is not actually, in fact, true, or it doesn't have to be. All right, so our last big scientist to talk about is Niels Bohr. And his model is probably going to look very familiar to you. He came along a very few number of years after Rutherford. This started to pick up very quickly. And he created the Bohr model, or the planetary model. These are two names for the same thing. It's named after him. He's two names for the same thing. Bohr, because Bohr discovered it, and planetary, because it kind of looks like the solar system, right? If this nucleus here in the center were our sun, then these electrons orbiting around the outside of it, those would be like the planets. So it's the planetary model. So Bohr only made a pretty minor change to Rutherford's model as far as what it looked like, but it's huge as far as what we know now about atoms. So he took all of those random electrons organized outside of the nucleus in Bohr's model, right? Bohr just sort of, not Bohr, Rutherford just sort of scattered his electrons all around the nucleus. And Bohr said, I don't think that's right. I think they are in specific orbits. And I think those orbits have fixed energy. This is what we're going to spend all of Unit 3 talking about, is how electrons behave. So Bohr organized the electrons. And while this is probably what you learned atoms look like when you learned about them in middle school, and while this is truly how we're going to draw atoms for most of this unit, it's not actually what they look like. So in the mid-1900s, a lot of different scientists were studying what is up with electrons. De Broglie, Heisenberg, and Schrödinger are just a few. Einstein talked about electrons. So many scientists talked about electrons. They all kind of elaborated on this idea of Bohr's orbits. And they said, well, that's nice, and it's very organized, and it's nice to look at. But this circular orbit situation is only true for hydrogen. So they came up with this model, with the nucleus still in the center, and all of these weird like balloon-shaped regions where the electrons are likely, not necessarily for sure, but they're likely to hang out. And these balloon-shaped, probably gonna find an electron there regions are called orbitals. Like an orbit, but different. And again, we're going to spend all of Unit 3 talking about these. So for right now, just please be aware that while this is how we will draw our atoms, because this is easier to draw, easier to look at, it's really a lot more complicated than that. All right, so at this point in your book, you've got a little bit of practice, a little bit of comparing and contrasting your different scientists. Take a minute, work these over with your group, and when you're ready to check your answers, go ahead and unpause the video. All right, hopefully this is what you came up with as your answers for the first two. And then your timeline is on the next slide. So if you haven't finished filling out your timeline, go ahead and re-pause. Make sure you've got your timeline all filled out. All right, and hopefully this is what you came up with on your timeline. You need to know the name of the scientist. You need to know the experiment they did, so cathode ray tube and gold foil. If their model has a name, like the plum pudding model or the planetary model, which again is the same as the Bohr model, you need to know the name and you need to know what it looked like. This is sort of what you're expected to know for each scientist. So if you've gone through this, if you've worked this out together and you are feeling good about it, it is time to move on to the last part of this video, which is about Coulomb's law. And as I said at the beginning of this video, Coulomb's law is an all semester. Well, it's really an all year thing, but we are going to talk about Coulomb and his description of a relationship all semester. Every unit, all semester. Unit 4 is going to entirely revolve around Coulomb's law. So get comfortable with him because he is here to stay. Coulomb's law is a fundamental relationship between electrostatic attraction and repulsion, which sounds very complicated. Here's what it means. Opposites, can you guess what the next word is? Attract. And like charges repel. That's what it boils down to, is this right here. Obviously there's some finer points, but essentially Coulomb's law, opposites attract. This applies to charged particles, which is largely what we're going to be talking about, right? Protons are charged, electrons are charged, they interact. But it also applies to things like magnets. It applies to gravitation between planets and very large bodies. It applies to all kinds of stuff, but we're really going to care mostly about our charged particles. All right, so in chemistry, as we just said, we're mostly interested in the energy of this attraction or repulsion, not so much a force. Coulomb's law technically talks about force. We care more about energy, specifically the energy between charged particles. Ooh. If and when you take physics, you'll see a different version of Coulomb's law. We're using sort of a modified version of it. And that is this right here. E, or energy, is proportional to, this guy means proportional to, Q1 times Q2 divided by R. And this equation is not given to you on your formula chart. This relationship you need to memorize. Again, we're going to use it so much that you will probably accidentally do that, but you do need to know it. It's not on your formula chart. So, each of these things. E is the energy of attraction or repulsion between particles. Bigger energy, bigger E value. Q1 is the charge of the first particle, so like the nucleus. And Q2 is the charge of the second particle, so like an electron. These are not the only things that Q1 and Q2 can be. This is just an example. And R is the distance between those charges. So if we had like a positive, this would be Q1. And if we had a negative, this would be Q2. And the distance between them, that is your R value. So as far as relationships here and things to really be able to take out of Coulomb's law, two simple rules for Coulombic attraction and repulsion. First, the energy of attraction or repulsion increases as the magnitude is size, of the charges increases. Right? We got E is proportional to Q1 times Q2 over R. So as these values get bigger, this value should get bigger. When the top of a fraction gets bigger, the fraction as a whole gets bigger. On the flip side of that, the energy of attraction or repulsion will increase as the distance between the charges decreases, right? Because we are dividing by this r, by this distance. So when you divide by a smaller number, when the distance decreases, the overall fraction gets bigger. We used this sort of similar math during density. So sort of 2 rules of thumb instead of remembering all of these many words. All you need to remember is this: big charges, big energy. Big distance, little energy. Because your R value, your distance, and your energy, these are inversely proportional, right? One goes up, the other goes down. But your charges and your energy, those are directly proportional. One goes up, they both go up. So examples, things you may see with this. Will an electron be more attracted to the nucleus of a hydrogen atom or of a helium atom, and why? Well, if you look on your periodic table, you will see the square for hydrogen has a 1 right there. And the square for helium has a 2. So in this video, we have not talked about the periodic table. When you come together with your group 1 people, they'll be able to explain this to you a little bit more. But this number up here tells you the number of protons in any atom. So hydrogen has 1 proton. It has a charge of +1. Helium has 2 protons. It has a charge of +2. So you've got your negative electron right here. You've got your +1 charge over here, and you've got your +2 charge over here. Well, remember, we said a second ago that as you increase your charge, you increase that energy of attraction or repulsion. So this relationship has more charge going on in it than this relationship. So this electron is going to be more attracted to this bigger charge. So it'll be more attracted to helium. Because helium has a nuclear charge, has a charge in the nucleus of +2, because it has 2 protons. So this is an energy of attraction because these are opposites, right? And opposites attract. But if this had all been positive, if we had a positive here in the middle, then this would be the greatest repulsion right here, because bigger charges increase the energy, no matter whether it's energy of attraction or repulsion. Opposites attract. It's still a thing. All right, so at this point, you've got some practice in your booklet, right? A little bit of distance, a little bit of attraction, a little bit of repulsion, a little bit of charge size, some multiple choice, sort of cover all of your bases. Work this out in your group. Talk to your other group 2 people. Work it through together, compare your answers, and then when you are ready to check, go ahead and unpause the video, make sure you did it correctly. All right, hopefully this is what you got as your answers. If it's not, talk it over with your other group members. Make sure you're very much on the same page, because it's probably time to go ahead and head back and teach this to the group 1 and the group 3 people in your group. It's probably time to teach this to the station 1 people and the station 3 people in your group. So you need to be comfortable with it in order to teach it to them. So make sure you've got this down. If you have questions, ask me questions. and get ready to head back and teach your classmates. If you're watching this at home, you obviously don't have a group. It probably means you're ready to move on to station 3. So good luck and have fun.